Good evening, everybody. So, this is our fourth lecture in pipe flow. In the first three lectures, we discussed on Reynolds experiment, energy losses in pipe flow, both major and minor losses. In the third lecture, we derived the equation for friction loss, major loss, that is Darcy-Weisbach equation. So, we discussed on Reynolds experiment, energy losses, both major and minor, and Darcy-Weisbach equation. So in today's lecture, let us focus on some of the problems in this particular pipe flow based on what we have discussed in the last three lectures. Right? Let me take you directly into the problems. Problems. Before I take up the problems, what is the what are the equations that we also should know before taking up problems at this stage? The first one is the major loss, head loss due to friction is equal to FL V square by 2GD. Right? If friction factor value is given, directly you can calculate HF. If friction factor is not given, then F can be calculated, and the equations for the F already I have given in the previous first lecture itself. But again, I will tell, if Reynolds number is less than 2000, use basically F is equal to 64 by RE, where RE is equal to rho VD by mu R VD by kinematic viscosity. If suppose RE is greater than 4000 and less than 10 to the power of 6, then RE is F is equal to F is equal to 0.316 divided by RE to the power of 1 by 4. There is one more formula. If RE greater than 10 to the power of 6, that also you have given already to you. But most commonly, these are the two. But if F is given, then there is no discussion. Straight away, substitute and get HF. Or if HF is given, get V or Q. So this is the problem. So this is one of the things. Or if minor losses are given, generally the minor losses already I mentioned in the last class. Minor losses are, even though there are many, but let us go for head loss at the entrance, 0.5 V square by 2G. Then head loss at exit, that is velocity head. Head loss due to sudden expansion So if you take this immediately, you should be able to draw. So here it is V1, here it is V2. If you take it, then it is V1 minus V2 whole squared by 2G. Then fourth one, head loss due to sudden contraction is equal to, if you take it, suppose here it is V1, here it is V2 basically, then in that case it is zero point 0.5 V2 squared by 2G. At least these four. So finally, what equations you should remember? Major loss is equal to FLV squared by 2GD. Minor loss is head loss at entrance is equal to zero point 0.5 V squared by 2G, and head loss exit is equal to, for example, V squared by 2G, and head loss due to sudden expansion is equal to V1 minus V2 whole squared by 2G, and head loss due to sudden contraction is equal to zero point 0.5 V2 squared by 2G. If you know this, some of the first the problems can be solved as a first phase problems. So let me take easy problems and let us introduce to you first. So the first problem I am taking, it is a pipe 200 mm in diameter and 45 meters long, conveys water at a velocity of 2.5 meters per second. Find the head lost due to friction. F is equal to 0.024. So straight, let us go into the solution. What are the given things actually? D is equal to 200 mm. So it is equal to zero point 0.2 meters. Then L is equal to 45 meters. V is equal to 2.5 meters per second. F is equal to 0.024. Use the equation HF is equal to FLV squared by 2GD. F is equal to 0.024. L is 45. V is 2.5 divided by 2 into 9.81 into diameter is zero point 0.2. So that gives you the solution of 1.72 meters. That is the head loss due to friction. Let me take another problem. A smooth wrought iron pipe 200 dia conveys crude oil at a velocity of 3 meters per second. Find the loss of head per 100 meters length of pipe. The kinematic viscosity of crude oil is zero point 0.5 Stokes. Find the loss of head per 100-meter length of the pipe. Now, one after the other, let us take what is given actually. Diameter is equal to 200 mm. So, zero point 0.2 meters. Then what velocity is equal to 3 meters per second. L is equal to 100 meters length. Then what he wants actually, kinematic viscosity is equal to zero point 0.5 Stokes. So immediately what I will do, zero point 0.5 into 10 to the power of minus 4 meter square per second, right? Converting into the units. Then, so problem is what he wants, how much is the head? Here problem is F is not given. So what should I do if F is not given? I must calculate Reynolds number. Then calculate, then Reynolds number is equal to how much? We know Reynolds number is equal to rho Vd by mu, or it is equal to Vd by nu. So V is given 3, diameter is equal to zero point 0.2 divided by zero point 0.5 into 10 to the power of minus 4. So the Reynolds number which we are getting, it is equal to 12,000. That is Reynolds number greater than 4,000. Therefore, F is equal to 0.316 divided by Re to the power of 1 by 4. Just now I have given the equation to you. Therefore, F is equal to 0.316 divided by 12,000 whole to the power of 1 by 4. So calculate F. If I calculate F, I am getting it as 0.03. So therefore, HF is equal to FLV squared by 2GD. So F is how much? 0.03. L is 100 meters. V is equal to 3 square. Then divide by 2 into 9.81 into D is equal to zero point 0.2. So if you calculate that, we are getting around 6.88 meters. This is next. I will take you into another problem. So the another problem is, for example, glycerin of viscosity 0.835 Newton second per meter square flows through a 150 mm diameter, 40 meters long pipe of wrought iron at a velocity of 3.25 meters per second. Find the loss of head in the pipe. Take density rho of glycerin is equal to 1260 kg per meter cube. So this is what he has given. Again, what are the given things? Let me take it. Mu is equal to how much he has given? Mu is equal to 0.835 Newton second per meter square. This is first. D is equal to 150 mm. So 0.150 meters. L is equal to 40 meters. Velocity V is equal to 3.25 meters per second. What is HF? This is the question. But again here F is not given. So calculate RE. RE is equal to rho VD by mu. Rho is 1260 he has given. V is equal to 3.25. D is equal to 0.150 by mu is equal to 0.835. So you are going to get how much actually if I do this, it is 735.63. That is Reynolds number is less than 2000. So naturally the flow is laminar flow. So for laminar flow, what is F is equal to 64 divided by Reynolds number. So 64 divided by 735.63. So that will be 0.087. So therefore HF is equal to FLV squared by 2GD. So what is that FLV squared by 2GD? F is equal to 0.087 into L is equal to 40 into V is equal to 3.25 whole square divided by 2 into 9.81 into diameter is 0.150. So this is equal to 12.49 meters. So this is another problem which we are taking it up. So now I will take another problem basically. So wherein we calculate the minor losses also in addition to the what you call it as the major loss. So how I will do? Water is discharged from a large reservoir to atmosphere through a 10 centimeter diameter and 500 meters long pipe. Find the discharge if the outlet is 15 meters below the free surface of water. In the reservoir. Assume the entry is Sure. Okay. F is equal to 0.04. Water is discharged from a large reservoir from a l- one second, large reservoir to the atmosphere through a 10 centimeter diameter pipe and 500 meters long pipe. Find the discharge if the outlet is 15 meter below the free surface of water in the reservoir. So if I try to explain to you by drawing a figure. So let us take this as a tank. Now this is the pipe and this pipeline length is L is equal to 500 meters, right? Then it is this diameter is equal to P is equal to 10 centimeters. That means zero point 0.1 meter. Then next, if I take it here, the water level here, from here to the outlet, if I, this is the outlet. So what is this actually he has given? This is given it as 15 meters. What is meant? So here, if it is 15 meters is there, for example, by the time the water comes to this point, right, total head is lost. When it is basically going into the atmosphere means then once it enters into the atmosphere, what is the velocity? Actually its velocity is zero, so that means total head is lost. So that means what is the meaning between these two is this is the outlet, this is water level in reservoir. So by flowing a distance of 500 meters, the total head is lost. So now remember this total head H, basically if I call it as this, we call it as H, right? This is the total head lost. That is equal to what he has mentioned, it is equal to 15 meters. Then what he wants actually from us, calculate Q. So now if I take it from here, right, from the beginning, if I take it, so what is the loss here? It is entry loss. From here to here, what is the loss? Friction loss. Then at the end, what is the loss? Exit loss. And I know the equation for this. So the total head is equal to entry loss plus friction loss plus exit loss. Meaning is H is equal to head lost at entrance plus head loss due to friction plus head actually loss at the exit. So if I write it, what is the head loss at entrance? zero point 0.5 V squared by 2G plus what it is here, FLV squared by 2GD plus what is exit, it is V squared by 2G. So therefore, if I make it H is equal to, for example, it is FLV squared by 2GD plus 1.5 V squared by 2G. Why this 1.5 V squared by 2G? This is the minor loss. Why minor losses we considered? He already given in the problem, assume the entrance is short. That is why we have considered this minor losses, right? Now, if I take it in this problem, so for example, now H is equal to 15, F is equal to 0.04, L is equal to 500 into V square divided by 2 into 9.81 into diameter is zero point 0.1. So this is first thing, plus 1.5 v square by 2 into 9.81. If I equate it, so except v, everything is known. So now I calculate, then v is equal to, if I do, I will get it as 1.21 meters per second. Therefore, q is equal to a into v. That is pi by 4, d square is 5 into 1.21. So this is equal to 0.0095 meter cube per second. So this problem can be solved in this fashion. So here I try to solve the friction loss, entrance loss, exit loss. Three I have taken. Now similarly you can do even for sudden expansion and sudden contraction also you can try it. Now after this class, my request to you is you take any problem even on sudden expansion, but equation for sudden expansion or sudden contractions are already given. So using those equations, you can try for sudden expansion and sudden contraction also. So I have solved basically in this lecture. So these are the problems which I have solved in this class. Work more, practice more problems. The more you do, naturally it will be very easy for you to do in the exam within time, basically. Because time management is a very, very crucial thing in the examination. Unless you practice, whether it is derivations or problems, you will not be able to really write within the time. So the only solution for this is write, practice, 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 and then basically you will be able to really manage the time very well and get the maximum marks. With this I will stop this lecture and let us discuss then the next lecture what about the hydraulic gradient line and energy gradient line or total energy line. With this, thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.